Hello and welcome to a not-so-average cooking show. Today we're going to be talking material science, specifically imperfections in solids. I'm going to be using some common household items to describe what's going on today. Now, due to a lovely force known as entropy or disorder, there is no such thing as perfect order in nature. Therefore, crystalline defects or irregularities in lattice sites at the atomic level are very prevalent. There are many types of defects in solids. We start with point defects, or 0D defects. From here we move on to line defects, or 1D defects. And next are interfacial or grain boundary defects, which are 2D. And from here we have voids and inclusions, or 3D defects. However, that is kind of in the next section of this course. A material's properties can readily change with microscopic defects, which is why it is such an important topic in material science. Now let's talk point defects. A vacancy is basically exactly what it sounds like. See these donut holes? They make a lovely basic solid, and when I remove one of these atoms from the lattice site, there's a vacancy. Now, a self-interstitial is basically the exact opposite. An extra donut hole, or atom, will crowd into an interstitial void in the crystal structure. This will create a larger distortion to the structure and also requires more added energy. Intentionally creating impurities in a metal's structure is called an alloy and is usually done to improve a metal's properties, like its ductility or strength. Two things can happen when impure atoms are added to a metal. It can become a solid solution, or you'll get a secondary phase, which is something that we won't really focus on today. A solid solution forms when a solute is added but the solvent's overall crystal structure is still maintained. Now, there are two mechanisms for which this can happen. Substitutional, where a solute atom replaces one of the solvents, or interstitial, where solute atoms make a home in the spaces between the solvent's crystal structure. The four Hum-Rothery rules control the degree at which solid solution can happen. The first is atomic size. This is where the radius of the solute minus solvent is less than 15%, otherwise it will go into second phase. Now next is crystal structure. Both crystals need to be about the same structure for this to work. Third, the electronegativity of the atoms have to be similar, otherwise, again, secondary phase will occur. Lastly, solvent wants to dissolve solute metals with higher volume. Next, let's talk linear defects. Now, linear defects are 1D misalignments of atoms and are brought on by dislocations. An edge dislocation is when an extra half plane of atoms are added into the lattice. You can see here in this Oreo, I've added an extra half of an Oreo cookie, and what would generally happen is the extra double step icing and this other cookie would like to kind of fall into the spaces in the lattice site, thus creating distortions. Now, a screw dislocation is a completely different idea. Think mechanics of materials. The lattice itself is sheared, thus creating a higher point and a lower point. Now, when you zoom up in on this, if you start on the high point of the lattice and walk in a circle, you will inherently be one step lower on the other side. If you continue this all the way throughout the cookie, that is kind of creating this helical pattern, sort of like the threads of a screw, and that's why it's called a screw dislocation. It is most common to have both types of deformations happening in a material, and it's usually caused to solidification, plastic deformation, or thermal stresses. Alrighty, 2D defects. Now, these are types of defects that occur between an external surface, such as air, or other crystals. An external surface defect happens when surface atoms have a higher energy state than others. This can be seen in this solid lattice made out of M&Ms, where the surface atoms here are not fully bonded like the others. Next, we're going to talk about grain boundary defects. Now, grain boundary defects occur when the meeting region between two meeting crystals is slightly mismatched. Now, this is due to irregular bonding and can have a high cost in energy. Grain boundaries are area defects. As you can see again with the M&Ms, this is where the grain boundary region occurs. The low density of the grain boundary creates high mobility, diffusivity, and chemical reactivity. Now to recap, solids will have imperfections. These microscopic changes to the atomic structure of a material will severely impact the material's macroscopic properties. This is usually beneficial, and defects can actually be induced to create desired properties. Thanks again for tuning in, and I hope you learned something about material science.